Considering individual penicillins that we will be covering in this course, there are three criteria that can actually be inferred from penicillin structures, which we will use to subclassify them. The first one is whether being orally active or can only be administered parenterally. The second one is the spectrum of activity being either narrow, broad, meaning that it includes more strains of gram-negative bacteria, or its activity can extend to include Pseudomonas. The third one is being sensitive or resistant to the effect of beta-lactamases. Resistance to beta-lactamases does, to a certain extent, contribute to broadening the spectrum of activity. Penicillins can also be classified into being either natural or semisynthetic. The only penicillins that are fermentation-derived, which we will be discussing, are penicillin G and penicillin V, while the rest are semisynthetic. These two penicillins are sensitive to beta-lactamases since they lack having a bulky group like a substituted phenyl or any other heteroaromatic ring that is directly attached to the amides carbonyl. As for the spectrum of activity, the two amide side chains are lipophilic in nature. They both lack having ionizable groups or highly polar groups, thus both are considered having a narrow spectrum of activity. The benzyl group in penicillin G is considered an electron-donating group, thus the beta-lactam is chemically unstable in acidic conditions. Yet in penicillin V, the electron-withdrawing group increases the chemical stability of beta-lactam, rendering it orally active. The next group includes methicillin and naphthalene. The amide side chains, which are dimethoxyphenyl in methicillin and 2-ethoxynaphthyl in naphthalene, are bulky, electron-donating, and lipophilic, which means that methicillin and naphthalene are beta-lactamase resistant, parenteral, and have a narrow spectrum of activity. Even though that the oxygens in dimethoxyphenyl and 2-ethoxynaphthyl are electron withdrawing inductively, yet at the same time they donate electrons via resonance. This can be well understood by drawing the resonance structures upon delocalizing the electrons lone pair on oxygen. In one of the resonance structures drawn in here, delocalization increases the electron density on the amide's oxygen, thus rendering the beta-lactam chemically unstable in acidic conditions. Since naphthalene has one electron donating oxygen versus 2 in methicillin, it is slightly more acid stable than methicillin. Although methicillin was a breakthrough in stability against beta-lactamases, yet bacteria found ways to resist it. An example is the emergence of the famous MRSA, which stands for methicillin-resistant Staph aureus. The ineffectiveness of methicillin against this strain is due to a mutation that led to synthesis of an isoform of a penicillin-binding protein, which is called penicillin-binding protein 2A, that methicillin has a very low binding affinity to. The third group includes oxacillin, cloxacillin, flucloxacillin, and diacloxacillin. The oxa is derived from the isoxazoyl ring, which is a bioisoster of benzene. The prefixes clo, flo, and diclo refer to the nature and number of halogen substituents on the benzene ring. The side chains in these penicillins are bulky, electron-withdrawing, and lipophilic, which means that they are resistant to the beta-lactamases, orally active, yet have a narrow spectrum of activity. Although the bulkiness of the side chain is what leads to the resistance against beta-lactamases, it lowers in a similar manner to methicillin its antibacterial activity against some strains of gram-positive bacteria. The electronegative heteroatoms in the isoxazoyl ring, along with the halogens on the phenyl, if present, contribute to the electron-withdrawing effect of these drugs' side chains, which renders them stable enough in the stomach acidic conditions, thus can be given orally. The high lipophilicity of the amide side chain leads to high protein binding, which exceeds 90%. This is important in infections where a high blood concentration of the free drug is needed, as in the case of septicemia. In such emergent cases, oxacillin would not be successful in eradicating the infection. The fourth group includes ampicillin and amoxicillin. The amide side chains in both aminopenicillins are not bulky, thus they are sensitive to beta-lactamases. Yet the lack of the inherent resistance to beta-lactamases can be compensated for by co-administration of beta-lactamase inhibitors. The primary aliphatic amine is a basic group with a pKa of around 7.5, thus it will be partly ionized at physiological pH. Protonation will make the side chain highly polarized and highly electron withdrawing, thus ampicillin and amoxicillin are orally active and have a broad spectrum of activity besides being sensitive to beta-lactamases. Alongside the huge electron withdrawal upon ionization, the positively charged side chain will lessen the chance of protonation of the beta-lactam nitrogen, which activates the beta-lactam prior to acid-catalyzed hydrolysis. This contributes even further in stabilizing the aminopenicillins, thus enhancing their oral bioavailability. Studies have shown that active transportation is another reason for the profound high oral bioavailability of aminopenicillins. The carboxylic acid, the beta-lactam, and the amide side chain, along with the alpha amino group, structurally resembles tripeptides, which make the aminopenicillins substrates for tripeptide transporters, which in turn will actively transport aminopenicillins to the inside of intestinal cells. In terms of the difference between ampicillin and amoxicillin, the latter has a phenolic hydroxyl. The reason behind such modification was to increase the isoelectric point value closer to that of physiological pH. The isoelectric point of ampicillin is 4.7. Ampicillin has two ionizable groups, the carboxylic acid on carbon 2 and the amino group on the side chain. When both groups are ionized, this is when the net charge in the molecule is zero. These zwitter ionic molecules that have the best absorption exist in a pH range of around 2.6 to 7.5, which are the pKa values of the two ionizable groups. The maximum percentage of the zwitter ionic molecules exist at a pH that is halfway through the two pKa's, which is 4.7. When having a third ionizable group, such as the phenolic hydroxyl in amoxicillin, that is weakly acidic with a pKa value of around 10, the isoelectric value shifts closer to the physiological pH value. This means that the percent of zwitter ionic molecules of amoxicillin at physiological pH will be higher than that of ampicillin. This will lead to increasing the rate and extent of amoxicillin oral absorption relative to ampicillin. Even though when ampicillin was developed, it had good oral absorption, its oral bioavailability was further enhanced via prodrug derivatization, as in the case of bivampicillin, talampicillin, and bacampicillin. Esterification of the carboxylic acid on carbon number 2 masks this highly polar group, which increases its permeability through cell membranes, thus its oral bioavailability, as you can see for bacampicillin relative to ampicillin in this graph. Hydrolysis of the ester via esterases releases a free ampicillin. The structure of the ester, where the hydrolyzable carbonyl is connected via an oxygen-carbon-oxygen linker to the carbonyl of the penicillin's carboxylate, is classified as an extended ester. Hydrolysis of the terminal ester is catalyzed via esterases. The intermediate form decomposes spontaneously, where the hydroxyl lone pair forms a double bond with the adjacent carbon, consequently breaking the carbon-oxygen bond in the linker, releasing the free drug along with gaseous formaldehyde. The rationale for designing extended esters is because the carbonyl attached to carbon 2 cannot be hydrolyzed efficiently due to steric shielding that is mostly due to the penicillin's nucleus, while that of the extended ester is reachable by the enzyme. Clavulanic acid was the first beta-lactamase inhibitor which was isolated from fungi. Clavulanic acid and other beta-lactamase inhibitors such as sulbactam and tazobactam, which are semisynthetic, have weak antibacterial activity. These compounds are irreversible inhibitors of beta-lactamases, which can be well understood upon investigating the mechanism. When a beta-lactamase inhibitor, such as a clavulanic acid, binds to the active site of their target enzyme, the serine residue attacks the beta-lactam, breaking it along with the bond between carbon 5 and oxygen of the oxazolidinone ring, forming an acyl enzyme complex. Since conjugated systems are more stable than non-conjugated systems. The imine tautomerizes to an enamine or an alpha-beta conjugated carbonyl. The resulting Michael acceptor is electrophilic, which can be easily attacked by any nearby nucleophilic side chain, represented here by N. The lone pair attacks the most electrophilic atom in the Michael acceptor, which is the beta carbon, forming a second bond with the enzyme. This will give rise to a very stable complex that its bond with the enzyme cannot be broken and the enzyme is irreversibly inhibited. Thus, beta-lactamase inhibitors protects co-administered penicillins from being inactivated by these enzymes. Other beta-lactamase inhibitors, such as sulbactam, react with the active site of beta-lactamases in the same manner. This figure summarizes the interactions of beta-lactams with the transpeptidases and beta-lactamases in comparison with that of beta-lactamase inhibitors. The acyl bond that beta-lactams form with the transpeptidases is stable, yet the one formed with beta-lactamases is unstable, which guarantees regeneration of the inactivating enzyme. Yet this hydrolyzing enzyme is irreversibly inhibited by beta-lactamase inhibitors due to the formation of very strong bonds with the active site. The last group includes carboxypenicillins and acyluredopenicillins. Carboxypenicillin subgroup include carbonicillin and ticarcillin. The side chains attached to the amide are not bulky. There isn't a phenyl ring or a heteroatom ring attached directly to the amide's carbonyl, thus these two compounds cannot resist beta-lactamases. The carboxylic acid on the alpha carbon is an acidic functionality with a pKa that is close to 4. Thus, it will be predominantly negatively charged. This will highly increase its polarity and electron density, rendering it electron donating. For those reasons, carbonicillin and ticarcillin have a broad spectrum of activity, yet not orally active. One issue seen with carbonicillin is epimerization. The acidic alpha proton in carbonicillin undergoes deprotonation in vivo, resulting in formation of a carbanion conjugate base, where the alpha carbon is sp2 hybridized with a planar geometry. This means that reprotonation of the carbanion intermediate, which have equal chances of being added from above or below the plane of atoms connected to the alpha carbon, results in either regeneration of the alpha R stereoisomer or epimerization of that chiral carbon to the S configuration. Thus, having an enantiomerically pure stereoisomer of carbonicillin is not a necessity. The other issue that is seen with carbonicillin but not ticarcillin is decarboxylation in stomach acidic conditions. The amide's carbonyl, being alpha to the carboxylic acid, will facilitate its elimination since the resulting conjugate base can be stabilized via resonance with the amide's carbonyl. The intermediate formed tautomerizes to give penicillin G, which is relative to carbonicillin, inferior in terms of its spectrum of activity. Esterification of the carboxylic acid, such as in the case of indenyl carbonicillin, prevents decarboxylation, thus it can be given orally. Ticarcillin, for a reason that is not well understood, does not undergo decarboxylation, thus it has replaced carbonicillin and indenyl carbonicillin. The other subgroup of beta-lactamase sensitive, broad-spectrum, and parenteral penicillins are the acyluredopenicillins, which include azlocillin, meslocillin, and piperacillin. Acyluredo means that the substituents on the alpha carbon structurally resembles an acyl connected to a urea, as in the case of azlocillin and meslocillin, or a derivative of urea, such as oxamide, aztine, and piperacillin. These substituents are not rigid bulky groups, thus these drugs are liable to beta-lactamases. The many nitrogens and oxygen atoms in the side chains that are hydrogen bond donors and acceptors is responsible for the increased polarity, which in turn increases the spectrum of activity against the gram-negative bacteria. Actually, the spectrum of activity of acyluredopenicillins is the broadest of all penicillins, and extends to include anti-Pseudomonas activity. The reason for that is believed to be due to longer side chains that can penetrate deeper in the active site of transpeptidases, forming more interactions with the target enzyme and consequently increasing their binding affinity and their antibacterial activity. The spectrum can be further extended by co-administration of beta-lactamase inhibitors to include resistant strains. In terms of the oral activity, the acyl group is liable to acidic conditions and undergoes hydrolysis in stomach acidic conditions, thus can be only given parenterally.